start this then. So 10.2, we're talking about sine and cosine, two of the 6 trig functions that we're going to study. And so what I said the definition was, it comes from the unit circle. So when we have an angle, and we think of angles as rotations, right? We talked about an initial side, and we also talked about what? The terminal side, okay? And the terminal side is going to be pointing somewhere, and it has to intersect the unit circle somewhere. And wherever, so if I have an angle theta, wherever the terminal side intersects the unit circle, the coordinates of that point, the x-coordinate is the cosine of theta, and the y-coordinate is the sine of theta. And it looks like last time I did the cosine of pi over 3. See, you can get that by looking right at that unit circle. So you guys were filling this out. Pi over 3 is the same as how many degrees, by the way? 60 degrees, right? So up here we had 60 degrees. Up here we had pi over 3. And last time when I filled this out, I took a lot of time and I showed you 30, 60, 90 triangles and that kind of a thing. But eventually you just want to memorize the numbers that go in there. And the two numbers that go in there are 1/2 and the square root of 3 over 2, right? Which one's which? Yeah, because 1/2 is smaller than square root of 3 over 2. That's how I remember it. Square root of 1 over 2 is less than square root of 3 over 2. So this one must be the 1/2, and this one must be the square root of 3 over 2. Right? So some of you were able to fill that out as you were working, as I was getting myself set up this morning. So now if I ask you, well, what's the cosine of pi over 3, what would I say? Sure, it's the x-coordinate. The cosine is the x-coordinate of where the terminal side of that angle hits the unit circle. And when I'm looking here, I see 1/2 as the x-coordinate, so the cosine of pi over 3 is 1/2. Okay? So when I say you need to know the unit circle, well, if you want to know sine and cosine, you really do. You have to know the x and y coordinates of all these points for these important angles. Okay? So we're going to go ahead and do some more examples. I'd like to try problem 2, and I'd like to try problem 4 from your book. And so again, this is page 736. It says, find the cosine and sine of the given angle. Well, what I'm really saying is, find the x-coordinate and the y-coordinate of the given angle, right? So I was asked to do pi over 4, and I was asked to do pi over 2. Okay? So if I go back to the screen and I say, well, I have pi over 4 and I have pi over 2, right? Well, the cosine of pi over 4 and the sine of pi over 4, I will know if I know the x and y coordinates that match that on the unit circle. Here, I'll do those in green. Here's pi over 4, same as 45 degrees. And what do you have for the cosine, and what do you have for the sine?
2 over 2.
Yeah, we talked about that one in that first day of class also. That's square root of 2 over 2, square root of 2 over 2. Okay? So I go ahead and I say, well, square root of 2 over 2, square root of 2 over 2. I'm going to pause and let you guys do number 4. That should take no time at all. We could all get that. Go ahead and make sure you can get the cosine and the sine of pi over 2. Remember that the key fact is that pi over 2 is the same as 90 degrees, because pi is the same as 180 degrees. So if I go ahead and we can't see that now. So when I'm thinking about 7 pi over 6, I know, and I'll do this one in red, I guess. This one is pi, okay? 7 pi over 6 is another pi over 6 down here, okay? And so you have to think a little bit about what the coordinates would be. And again, if I understand that this one here is square root of 3 over 2 1/2 when I'm at pi over 6, what I might understand is that I'm rotating the same amount past pi, another pi over 6, okay? And so you say, what would the coordinates be of this point? Well, they're very similar to what you have here. What's the only difference?
Negative.
You have some negatives, right? Because I'm in quadrant, what quadrant is that?
3.
Quadrant 3. So both the x and the y coordinates are going to be negative, okay? And so I'm going to have negative, and what are these things? Well, negative square root of 3 over 2 and negative 1/2. And how do I know that's the right order? Well, what I say is square root of 3 over 2 is bigger. And so I notice that I'm moving farther to the left than I am down. So the x coordinate I would expect to be negative square root of 3 over 2, and the y coordinate is 1/2. And you could check that on the calculator. We showed that last time. That you could do these with a calculator if you're in the right mode, right? But these are things that we can also do without a calculator, and so I'm trying to show you how to do that. All right. Moving on, I want to try something more like 23. So we did 2, 4, 8. Let's move on to number 23. And so they're asking me the following. It says, well, hey guys, I don't know what theta is here, but I know that the sine of theta is 5/13. Theta is in quadrant 2. So let's go ahead and draw a picture of that situation. Theta is in quadrant 2. And so, well, theta is somewhere over here, okay, in quadrant 2. I'm rotating at least that much. And the terminal side, I'm going to say, is something like this, okay? And it tells me that the sine is 5/13. So is that the x coordinate or the y coordinate? That's the y coordinate, right? And so, you know, if I'm on the unit circle, I guess what I'm given is that the y coordinate is 5/13. That's this piece of the triangle. What I draw is what's called a reference triangle. Okay? The reference triangle. You always draw the triangle, so you drop a perpendicular to the x-axis. If you do it to the y-axis, you're going to get the answer wrong. So we want to drop it to the x-axis. Okay? And so I guess what I can say is, well, I know that this side of the triangle is 5/13. I know that this side of the triangle is 1. How do I know that? How do I know the hypotenuse of that triangle is 1?
The radius.
Yeah, that's the radius of the unit circle, right? Anytime we talk about sine and cosine, we're really talking about a unit circle. That's a unit circle, so we know that it's 1. And so I guess what's unknown here is this. I'll call it x. That x, right? X, of course, is the cosine of theta, and I'm given that the sine of theta is 5/13. So we want to come up with cosine of theta. Does anyone have it? Okay, so it's not an immediate. Oh, you have it? What do you have?
Negative 12/15.
How'd you get it?
I did it the way my brother taught me how to do it.
Okay. So what's your brother say?
Do inverse sine of 5/13.
Okay.
Take the cosine of that answer.
So you're going to use the inverse function, which is something we're going to get to. Okay. But I think down the road here, if I give you a different method than your brother, I think you're going to be happy. But that's nice. It's a nice approach. I want to stay away from inverse functions yet. So my picture of theta is this rotation. I know that the sine of theta is 5/13. And you notice the first thing is Tyler, right? No, Kevin. The first thing Kevin said is that his answer, he says x is negative. How many agree with that? You can tell right away because why?
Quadrant 2.
Quadrant 2, okay? There's a reason they told me the quadrant. Now the other thing is I guess I have to figure out what that x is. Well, one way to do it, what kind of triangle do I have here? Right triangle, so what can we write? Your favorite theorem, right? X squared plus,
Squared.
yeah, what's our y though?
5/13.
5/13 squared equals, hello? 1 squared. Now, would you believe me if I said we could solve that and we could get x and we would get 12/13? Actually, we'd have negative 12/13. You guys are going to take my word on that? Because I'll tell you what, I'm kind of like you. I don't like this equation. What's the thing about this equation that you don't like and I don't like? We don't like the fraction. We hate the fraction. It just drives me crazy. But see, there's another picture that solves the problem. So let's draw a new picture. And so we're going to draw a new picture of theta. Theta is in quadrant 2. So when we rotate, we're going, say, this far. Okay? But now what I'm going to do, there's my terminal side. Instead of just limiting myself to the unit circle, say that's the unit circle, right? Last time I stayed in the unit circle and I had the radius was 1. There's another way to do this. And that is what I'm going to do is I'm going to say that my radius is 13. Now why? Well, if I make my radius 13, then out here, okay, I can say that this is 5. And so this is another picture of sine of theta is 5/13. 5/13. I have a right triangle. But the reason this works is the right triangle, and here's a little geometry fact you might remember, the black right triangle is similar to this little red triangle, which is in the unit circle. This is 1, and this is 5/13. In other words, the black triangle is how many times as big as the red triangle? 13 times as big. But the ratios are the same. Okay? So we understand that usually in the unit circle, if I want the cosine of theta, that's x, and if I want the sine of theta, that's y. Okay? I understand that. But for an arbitrary circle of radius, I'll call it r, well, the sine of theta is not represented by y anymore. You see, this point over here, I don't know what point it is, but I know its y coordinate. What's its y coordinate? 5. And so the sine of theta is given by y over r. Does that make sense? 5/13. Now, the cosine of theta. What do you think that's going to be?
X over R.
X over r, where x is this distance on the right triangle. And it just makes the calculations nicer. Here, let's use the Pythagorean theorem. The Pythagorean theorem tells me x squared plus 5 squared equals what? 13 squared. And now I really wonder how much you remember from that geometry teacher or that algebra teacher. We had to memorize these perfect squares. I know you know what 5 squared is. Did you remember what 13 times 13 is? We had to know up to 25. Okay? If you don't know those, might be something worth memorizing. Okay? And so let's see what happens now. I'll subtract 25, so I get x squared equals, which is convenient, right? Because then x equals, well, wait a minute. There was a rule from algebra class. And the rule was whenever I take the square root of both sides, I also have to put plus or minus. Okay? So when Kevin said that the answer is negative, actually you all told me the answer is going to be negative. Here's the place where you make your choice. And so I would say that in this problem, x, which again is the cosine, well, x here equals negative 12, right? We chose the negative one because we're moving to the left. So now to finish the problem, if we want the cosine of theta, the cosine of theta is negative 12 over what? 13. And so that's my final answer here, negative 12 over 13. Two, they said cosine of theta is 4/9, and they say I'm in quadrant 1. And that's going to be important. Because it helps you find the sign of your sign. Hey, that's kind of weird, the sign of your sign. But if I'm in quadrant 1, I want to draw a triangle that's going to match, right? And so cosine, by definition, for an arbitrary circle, is given by x over r. So when you draw your picture, you probably come over 4. That's my x. And r is what? Well, 9, right? So my radius is 9. And so my right triangle looks something like that. The thing I don't know here is what? This y coordinate, right? And so I have 4 squared plus y squared equals 9 squared. 16 plus y squared equals 81. Y squared equals, you guys got 65 on that? Okay, so y is the square root of 65, which is not a perfect square. I guess it's a little more than 8, right? But if I want the exact value of the sine of theta, I would say that again, if this is theta, that the sine of theta equals, and what would I say? Square root of 65 over 9. Again, it's y over r. There it is. And again, I guess I glossed over a step. There's a plus or minus here. The reason it's a plus is because I'm in quadrant 1. I know that both of the coordinates have to be positive when I'm in quadrant 1. You guys with me? Okay. Let's move on. If you go to the next page, page number 32. No, that's the same page. Number 32. It's just down a little farther. Oh no, next page. So it says, find all of the angles which satisfy the given equation. Okay? This time, I give you what the cosine is. You have to find all of the angles which satisfy the given equation. All right? Talk to someone next to you, see what you guys come up with for a moment there. So you guys, I'm looking at negative square root of 3 over 2. That's a number I kept seeing on the unit circle. So I'm going to open to that page. It says I'm looking for the cosine. So am I looking for x or y coordinates? All right? And so I'm looking and I'm seeing right over here, here's an angle. 5 pi over 6. But did you notice there's more than one answer? What else do you have? Down here you have 7 pi over 6. That was the one we had earlier, right? Are there other answers? Let's see. I found that theta could be 5 pi over 6 or 7 pi over 6. But there are other answers, right? Because what about, 5 pi over 6? Let me do that one. That one I'll do in green, right? So that looks like this. It ends up in quadrant 2. But what about this angle that I'm going to do in red? Imagine this. Right? That's a rotation. The terminal side is ending up exactly the same place. The reference triangle would be the same. Now, how do you get that angle? I guess that would be 5 pi over 6 plus what? 2 pi is 360 degrees because pi is 180. 2 pi. Let's put a k. And let's say that k could be any integer you want. You could make k -1. That would be moving 2 pi the other direction. You could make k 10 and you get dizzy drawing it, right? But that's the deal. So 5 pi plus over 6 plus 2 pi k, or 7 pi over 6 plus 2 pi k. I guess this would be my way of representing all the angles such that the cosine is negative square root of 3 over 2. You guys follow? Okay. So I just have about 3 more examples I want to give you from this section. Okay? We're going to start with number 59 here. So read what it says. Theta is 12 degrees. The side adjacent to theta has length 4. How long is the hypotenuse? Okay? So I'm going to go ahead and try and draw that picture. So the first thing I want to do is draw theta. And they tell me that theta is 12 degrees. Well, 12 degrees, what quadrant am I going to end up in here? Quadrant 1. And so I'm going to go ahead and draw it. It's not very big. It's like maybe that far. And so my angle, I'll say, is 12 degrees. And then they tell me that the side adjacent to theta has a length of 4. Okay? Is 4. I should be more careful. Has length 4. So what that means is if I draw my reference triangle here, what do they mean, the side adjacent to theta? Well, they don't mean the hypotenuse. Okay? I mean, that's one thing to understand. They would say the hypotenuse. So your right triangle is going to have the hypotenuse, and it's going to have a couple of other sides. There's a side opposite and a side adjacent. Go ahead. The side that touches it. Yeah, adjacent, you might say, is touching. But that's 4. And now it says, find the hypotenuse. That's what they want? Okay. So the question is, how long is the hypotenuse? So I'll tell you what. Let's find x, where x is the hypotenuse. Okay? I don't know if you guys have seen that around the internet. Find x. They make t-shirts. Yeah. Anyways, there it is. No, we're supposed to go ahead and compute it, right? So what do? Well, we're going to use our trigonometry. So what I want to do is I want to write down a trig function. And remember my definitions, and maybe x was a bad choice here. I shouldn't use x. Let's use a better, smarter choice. what have I usually been calling the hypotenuse? The radius, r, right? Because when you rotate in a circular motion, see here, x is 4, right? That's the x. Let's call this r, and let's say we're going to find r. Okay? So now what I'm going to say is, do you think I should use cosine or do you think I should use sine for this problem? Cosine, because my definition is that the cosine of theta is x over r. Okay? So you're right, we're going to use cosine here. And I know my theta. The cosine of 12 degrees is equal to 4 over r. What I don't know is r. But that's an algebra equation. We can actually solve for r. So I'm going to go ahead and do that. By the way, how do you solve an equation like this for r? What I would do is get the r out of the denominator. I would multiply both sides of this equation by r. On this side it cancels. So now it says r times the cosine of 12 degrees is equal to 4. Okay? And so r equals 4 divided by the cosine of 12 degrees. And there's the answer. And if you have a calculator, now I want to take it out and come up with an approximate answer. Okay, so I'm going to turn it on. And let me go to the home screen. I'll clear it. And what I want to make sure is that I'm in the right mode. So for me, the mode key is right next to the yellow second key. And, okay, yeah, I'm in good shape. If you notice the third line down there, it is in degree mode right now. Okay? Normally it starts in radian. That's why it's been pushed over to the right. So I'll hit second quit, and now I'm ready. And so I'm going to type in 4 divided by cosine of 12. So that's 12 degrees, not 12 radians. And so according to this, the radius is, well, 4.089, okay, approximately. And does that make sense? Should it be a little bit more than 4? Well, yeah, because if you have a real small angle, right, we know the hypotenuse is a little longer than that side. Okay, just a little bit. Guys follow? See, what if I had been in radian mode? What would have happened? Let me just show you that. Put it in radian mode just for fun. And let me just hit second entry, which gives me the exact same thing back. Now I get 4.74. I might think that's the right answer, but it's not. Okay? So you got to be careful about your mode. Make sure you check for a given problem. Are we in radians or are we in degrees? That's going to be a question you ask yourself all semester. But again, we're going to use radians, I'd say, more often. We use degrees sometimes when you have a physical situation, you know, because it's not like we measure in radians when we're measuring angles in construction, let's say. Okay? So that's kind of the two situations we're going to deal with. So for 57, let me just scroll up and we can see this triangle. I'd like to copy this triangle down, and it says to find all kinds of things about it. Find alpha, A, and B. So they use the Greek letter again for the angle. So they say angle alpha is this angle on the upper right. What about that 8? What's the 8 here? That's the hypotenuse. Okay. They give me 33 degrees for one of the angles. They also give me 90 degrees for one of the angles. So we ought to be able to get alpha, and then hopefully we can get A and B. All right? So let's go ahead and try and do this. And by the way, one thing that I should point out, this is very common. The Greek letter alpha corresponds to our letter A. The Greek letter beta is B. So alpha is across from the side labeled A. And we're going to do that quite often. Okay, alpha, beta. So All right, so I want to go ahead and find some things here. Alpha equals, help me out. How'd you get that so fast? We know that all three angles have to add up to what? 180. So actually, before I write that, let me just write it down that we know that alpha plus 33 plus 90 has to equal 180. So alpha plus 123 is 180. And if I subtract, I get 57 degrees. I think it's 57, right? Yeah. So now I need to come up with A or B. All right? And so, oh, this is where it gets a little confusing maybe. I mean, I've been using these definitions. Cosine of theta is x over r, and sine of theta is y over r. But that only works if your initial side is the x-axis and you're rotating in the counterclockwise direction. See, when you get to this situation, like I'm dealing with angle alpha, let's say, or I'm dealing with 33 degrees, let's say, it's hard to know which side is initial and which side is terminal. And this is where there's a better definition, okay, to help me work here. I'm going to say that cosine is always adjacent over, what does R stand for? Hypotenuse. And the sine is opposite over hypotenuse. And I'm going to guess that some of you have learned those definitions before. Good old SOHCAHTOA. How many people have heard that before? SOHCAHTOA. All right. So it still is allowed. It's still valid. It matches up nicely. And so in this kind of a problem, I'd go ahead to that. SOHCAHTOA. Okay? In other words, so we have to decide which angle we want to use. Should I use 33 or 57? Okay, I'll use 33. So I'm going to say, for example, the cosine of 33 degrees is equal to, what would I write? A over 8. You see that? Because A is the adjacent side and 8 is the hypotenuse. What about the sine? If I write the sine of 33 degrees, that's B over 8. And so there's two algebra equations that you can use now to solve for A and B, right? In other words, the first equation tells me that A is equal to, if I multiply both sides by 8, it's 8 times the cosine of 33 degrees, whatever that is. Let me work that out. I have a calculator right here. And it's in degree mode. I checked that just a minute ago. So I'll do 8 times cosine 33 degrees, and I get negative 0.106. Whoa. What happened?
Wrong mode.
I am in the wrong mode. I just did 33 radians. Remember? I was in degree and I switched to radians to see what would happen. So there's a dead giveaway that we better check. Degree mode. Boom. Okay, let's try again. 8 times the cosine of 33 degrees. That looks more reasonable, doesn't it? So we want to check the reasonableness of our answers. 6.71. Okay? And now I can do, well, the same thing, but I don't need 8 cosine of 33. Now I need 8 times sine of 33. And so B is 8 times the sine of 33 degrees. And that's approximately 4.35. And I guess, as an added check, what I could do is I could take this answer and square it, and I could add it to my 6.71 squared. Now I rounded here, but why am I doing this? I'm going to take my answer for A and square it and take my answer for B and square it and add them together. I got 64. Does that work? Because what do I want it to be? 8 squared, right? It's a right triangle. The Pythagorean theorem ought to work. So it seems like my answers are pretty good here. Guys follow? And it says find the equations of motion. See, you guys have to understand, when you have circular motion, that's modeled by these two functions, cosine and sine. And so in general, what I want for the equations, I'll have x equals cosine t and y equals sine of t. Cosine and sine. Because what happens is, if my motion is in the circular direction, okay, we know that we can model any point on the unit circle by cosine and sine. Right? So that's the unit circle. But we also know that if we have a different size circle, that in general, the cosine of, say, theta is x over r. Or another way to say it is that the x coordinate of this point, when the yo-yo is there, is going to be r times cosine theta. Right? We just did that. We solved for x. And so if I ask you what are the equations of motion, well, it turns out that there's two equations that kind of tell us the motion. Because theta changes as time changes. Okay? And so if I want to know what the x coordinate is at a given time, or what the y coordinate is at a given time, okay? If I understand how theta changes with respect to time, I can actually write r cosine of t and r sine of t. And those are going to give me the equations of motion. If you take a look in the book, just a couple pages, we have that here. It says if I have a constant angular velocity, oh, do you guys know that Greek letter? Not W. That's omega. If that's my velocity, omega, then the functions are given by cosine of omega t and sine of omega t. Let me throw that in. Instead of just t, let's write omega t, omega t. Because what I did was, I had to talk about the angle, theta. So here, theta is going to be omega times t. Omega is angular velocity. T is time. Okay? And of course, theta, that's our angle. We talked about angular velocity last time, but I wanted to make sure I went through this example with you so that you see it being used. Okay? So here I'm going to do it now. There's my picture so far. Let's go back to the book. It says, well, exercise 52 in 10.1. You guys may have worked on this for homework. I don't know. Where is it? In the yo-yo trick around the world, the performer throws the yo-yo as it sweeps out a vertical circle whose radius is the yo-yo string. It says the yo-yo string is 28 inches long, and it takes 3 seconds to complete one revolution. Compute the speed in miles per hour. Okay. So let's see what's going on here. So if I go back to what I know, it says we have a yo-yo. The radius is 28 inches. All right. So my string of my yo-yo is 28 inches, let's say. Okay? That's my R. That's the radius of my circular motion. R is 28 inches. What else did they tell me? It says assume that t equals 0. When time is 0, we were over here. This was when t equals 0. Now the thing's moving. And it says it completes 1 revolution in 3 seconds. Well, you know what that is? That's omega. Omega, in this problem, I have 1 revolution in 3 seconds. Okay? That's omega. And so now what we'd like to do is we'd like to write out the equations of motion. Okay? Now, for this to work, I need omega times t, where t is time. Okay? I'm going to leave t as kind of the input. Okay? This is actually really pretty. We want to be working in what units? Not revolutions. Well, they said miles per hour in the last problem, yeah. But the trig functions work best in which units, I said?
Radians.
Radians, okay? So here's a question. Can we change this from revolutions per second to radians per second? Well, yeah. You have to multiply by the right fraction. 2 pi, well, how did it work? 2 pi radians is the same as what? 1 revolution. You could also multiply by, pi over a half or something like that, but this works. So here, revolutions cancel. And so my omega that I want is really 2 pi over 3. Okay? So now the equations of motion, what are they? Well, x is a function of time, and it's given by, what's r we said? 28 times the cosine of 2 pi over 3, that's my radians per second, t, and y of t is given by 28 sine 2 pi over 3 t. Okay. And I'll be honest with you, I debated, do I want to show this today or do I want to wait for 7 weeks or 9 weeks when we actually get to what are called parametric equations? But I said, no, I want to go ahead and show it. You see, we can actually use these 2 equations and get a picture on our graph. And so I want to go ahead and do that. I want to draw a picture of the yo-yo. So to do that, I need to hit the mode button again that you're getting used to. Do I want to be working in radians or degrees here? We want to be working in radians. But then I want to go down one more level. I'm going to go here to where it says function, and I'm going to go one to the right. That's PAR. And that PAR stands for what are called parametric equations. This is something we're going to study at the end of the course. T is my parameter. But it comes up in calculus enough that I thought, hey, let's see it now. T stands for time. But basically, the x-coordinate depends on what the time is, and the y-coordinate depends on what the time is. And these functions, cosine and sine, help me to get it. So I'm going to change this to parametric mode. And now when you want to graph an equation, usually, what button do you press? For graphing, you guys have done this before. Don't you press y equals? I'm going to press y equals, but watch what happens. It says, hey, x and y, tell me what they equal. So where it says x, what am I going to write? 28 times the cosine, and now it says open parentheses. I need 2, and then to get pi, I'll hit second caret, divided by 3, times, and then to get the t, see this x button up here, where you normally press x? it says x comma t. Now if I press it, it actually gives me a t because I'm in parametric mode. You'll notice there's also a theta. That's for a different mode we'll do later also. You're going to learn a lot this semester. So there it is. 28 times the cosine of 2 pi over 3 times t. And then what am I going to type here? 28 times the sine of 2 pi over 3 times t. And if all were well with the world, when I pressed graph, I would see beautiful picture, but I won't see anything here. I did see, I don't know if you saw, I saw my calculator was trying to do some work here, but it didn't graph anything. Do you know why? The what? It's not in the window. The window is your common, Anna remembers from college algebra, we did this all the time. We have to adjust our window. And you notice what it gives me. It gives me T min and T max. It gives me T step. It gives me X min and X max. Well, that's what I have to change, are my X's and my Y's, because remember the radius? What's the radius of this thing? 28 inches, right? So I better change the X min and X max. Why don't we make them negative 30 and positive 30, and then I should be able to see what's going on. So here's 30, negative 30 to 30. And again, the Y's I'll also make negative 30 to 30. And now we should see, if I graph, I should see some nice circular motion. Actually, it went around twice because it goes around, well, however long the t you specify is. But you could see that yo-yo in action. Okay? That's a way of representing. These cosine and sine can be used to represent circular motion. That's kind of the point. Any questions?